So what we're interested in chemistry, we are interested in measuring energy changes for chemical reactions. So we've talked about how we define a system and the surroundings, and we've talked about how heat and work are the means by which energy is transferred from the system to the surroundings, or vice versa. Heat, Q equals mc delta T. Work is negative P delta V. So the change in internal energy during a chemical reaction is a measure of all the energy that is exchanged with the surroundings. And that equals heat and work. So we can say that delta E, the change in internal energy, is equal to Q plus W. Now, if there's no change in volume, what happens to W? It becomes 0, because W is negative P delta V. And if delta V equals 0, then W equals negative P times 0, which is 0. Right? If W is 0, then we end up with the change in internal energy for this reaction is equal to the heat, Q. And we put a subscript V there to mean this is the heat at constant volume. So we're choosing a condition where our equation gets simplified. It's not practical to look at individual reactants or individual chemicals in a reaction and see what their temperature change is, because they all get mixed together, right? So what we do is we set up system and surroundings so that we can measure the change in the surroundings. So sorry, lost my pointer. So the system is the chemical reaction, and we're interested in the amount of heat that is gained or lost by that. We can't measure that directly, but we can measure the heat gained or lost by the surroundings. Whatever is lost by the system is gained by the surroundings, and vice versa. So Q sys and Q surroundings are the same number, they're just opposite in sign. The negative over here does not mean that this number is negative. It just means that this is the opposite in sign of that one. So we set up the surroundings using a bomb calorimeter. And so the surroundings now are the calorimeter, and so that's equal to negative Q cal. Calorimetry is a technique where we measure the heat of a reaction by observing temperature changes in the surroundings, the stuff that's surrounding the reaction. So we've got the system, the chemical reaction that we're studying. We're doing this at constant volume, so there's no work involved. And so we're looking at the heat being transferred to the surroundings, and we can observe a change in the temperature of the surroundings. So this is what a bomb calorimeter looks like. This is the bomb in here. It's an airtight container that you put your sample in. This is set up for a combustion reaction. So we've got the sample in there. There's oxygen present in here because that's needed for combustion. We have ignition wires so that we can start it burning. It can't expand in volume, so the volume's constant. This is going to generate heat. This is our system. Where's the heat going to go? Into the surroundings. The surroundings is the rest of the calorimeter. It's full of water. We've got a thermometer here, and we've got a stirring mechanism. And this is well insulated so that we can be pretty confident that we're not losing any of the heat getting into that water. We're not losing it to the outside. Okay? So we measure the temperature change in the water, and we can calculate Q. So we've used Q equals mc delta T. Here we're going to use a calorimeter constant, which is really the heat capacity, not the specific heat capacity, but the heat capacity of the calorimeter. And that's measured separately. So we've got this constant times the change in temperature. That gives us the heat gained or lost by the calorimeter. And all of that heat came from the reaction. So that Q reaction is our Q volume, which is the change in internal energy of the chemical reaction. So let's look at an example. When 1.550 grams of liquid hexane undergoes combustion in a bomb calorimeter, the temperature rises from 25.87 degrees Celsius to 38.13 degrees Celsius. Find delta E reaction for the reaction in kilojoules per mole of hexane. The heat capacity of the bomb calorimeter determined in a separate experiment is 5.73 kilojoules per degree Celsius. So we've got some numbers here, and we need to write them down. So we've got 1.550 grams of hexane. So that's a mass. And we've got two temperatures. It says it's going from 25.87 degrees Celsius to 38.13 degrees Celsius. So the initial is the starting and the final is the ending, right? If it started at 25, that's our initial temperature, and this is our final temperature. So we can calculate the change in temperature, be 38.13 minus 25.87. 12.26 degrees Celsius. And then we also have that the C-cal is equal to 5.73 kilojoules per degree Celsius. So we've got hexane burning. It releases heat, energy, that's absorbed by the water in the calorimeter. The temperature of the calorimeter goes up, we can measure that. So Q-cal is going to equal C-cal times delta T. It's not MC delta T because this calorimeter constant includes the mass and the specific heat capacity of the calorimeter. The calorimeter is always the same, and so we don't need to use both of those terms in there. So Q-cal then is the calorimeter constant, 5.73 kilojoules per degree Celsius, times the change in the temperature, and the degree Celsius cancels out. So Q-cal is 12.26 times 5.73. 70.2498 kilojoules with 3 seconds. So that's a positive number because the calorimeter got warmer. It absorbed energy. Where did the energy come from? The reaction. But the reaction lost the energy, so the sign for Q on the reaction is negative, right? This is like, a monetary transaction. I'm moving $10 from my checking account to my savings account. When you look at the register for the checking account, it says negative 10. When you look at the savings account, it says positive 10. If I move $50 from the savings to the checking, then it's negative 50 in the savings and positive 50 in the checking, right? We all understand that. This is the same idea. This is the $10, the $50. This is the money going back and forth. The sign it will be different depending on what side you're looking at. If you're looking at the system or you're looking at the surroundings, the number's the same, but the sign is different. So for QCal, which is the surroundings, it's positive. QCal equals negative Q reaction. So if this is QCal, then we can also say that Q reaction equals negative QCal. Right? Just multiply both sides by -1. So Q reaction equals negative 70.2498. You okay with that? Does this answer the question? Well, we said that delta E for the reaction is equal to the heat at constant volume, which is what we've got going on here. But what do they specify? Kilojoules per mole of hexane. This is the amount of kilojoules when 1.550 grams of hexane reacts. Is that a mole of hexane? No. It's this much energy for this much hexane. So we could convert that to moles, right? We could do that. Sure we could. So we've got hexane, 6 times 12.01 plus 14 times 1.008. $86.172 grams per mole for hexane. So if I've got 1.550 grams of hexane, I could multiply, so I've got moles on top and grams on the bottom because I want the grams to go away. 1 mole of hexane weighs 86.172 grams. .0179872 moles. So it's this much energy for this many moles. If I take the kilojoules and divide by the number of moles, then I'll get the amount per mole. So I'm going to divide by 0.0179872 moles. $39.05. .5 kilojoules per mole. Anybody else get that number? You guys are letting your calculators rest, right? It's okay. So the number went up because this amount of energy was released for a very small, much less than 1 mole. If we burn an entire mole of hexane, we're going to get a lot more energy. We need to be careful when we round this because we're rounding in the tens place, and 3,905 is not even close to 390. So minus 0.3910 kilojoules per mole. Any questions? You could put that in scientific notation. It would be minus 3.91 times 10 to the third. Yes?
What was the reason you found the moles again?
The reason I found the moles is because the question asks me to find delta E in kilojoules per mole of hexane. And I've got this number, but it's for this amount in mass, in grams. Yeah. So I had to convert that to moles and then divide. Any other questions? Yes?
So like the mole was smaller, so the heat is more getting hotter.
Can you repeat their question?
Like that equation, if the mole get more smaller, so
Mhm.
it's surrounding this more hotter.
So this amount was released for an amount smaller than a mole. So when we burn a whole mole, we're going to get a lot more energy. Is that what you mean? Yeah. If this number was bigger, like if it was 5 moles, then when we found the amount per 1 mole, the amount of energy would be smaller.